So now in this video we're going to be looking at transistor gain. So this is a 2N2222 right here. I have 10 volts being supplied by the power supply. It has alligator clips that come up there, and they got little jumpers that I clip them to and plug them into the board, and then other jumpers. If I power one rail, the other rail is powered. But in any case, we got 10 volts there. You don't see any current, but there is a little current going through this trim pot there. And there's also a resistor. We'll probably get to why I have that resistor there later. But in any case, that's a 2N2222. Left pin is the emitter, middle pin is the base, and the right pin is the collector. I think you can see all three pins like that. I'm going to put the emitter where the one row down from that jumper. I'm going to put the base to that jumper. And so first we're going to look at why I have this set up here. So with the multimeter here, I'm going to set it, first I'll set it to milliamps of current. And so here you can see that we got a resistor to the positive rail. It comes to the trim pot. There's a resistive element there and a wiper. A wiper connects there. We can slide it across that resistive element. And so the middle pin underneath there comes to this jumper, and we put it to the base of the transistor. And we can see how much current that's going to put through the emitter to ground right there. So it looks like about 0.11 milliamps of current. I have the meter set to measure milliamps. We can get a more accurate reading by going to microamps. And by the way, the red probe stays there. And so, as you can see, this is very little current. So transistors are amplifiers. And so it takes the base to emitter current, which is 104 microamps. So a microamp is 1/1,000,000th of an amp. A milliamp is 1/1000th of an amp. So pretty low current. Not terribly low, but pretty low. Let's get the meter to milliamps right there. Now, why is that important? The current going through there determines primarily how much current can go from the current from base to emitter, I should say, determines how much current can go from collector to emitter. So later on we'll look at if there's no current going through there from base to emitter, then there'll be no current going from collector to emitter. We're going to take an LED and put the short lead, the cathode, where the collector is, long lead, the anode, up one row, and we're going to give it a 510 ohm resistor to the positive rail right there. And then that's going to go to the anode. And of course there is a ground connection there, but current will not flow that way from positive to the collector and then through the base to the negative rail. It just doesn't work that way. So we need to complete the circuit by connecting here. So I have this 2 milliamps. That's really important right now because we're going to get a lot more current. So this is going to be the current going through a collector to emitter. You'll see the LED light up, plus the current going from base to emitter. But the base to emitter current will be so much smaller that we won't notice anything. There we go. And so we have about 7.4. And you notice as the transistor warms up, it is letting through more current from collector to emitter. And that's about 77, 78, looks like, times the amount of current than what is going through the base emitter by itself. Right there, you see 0.1 right there. And we had about 78. And so, that is not the current that the LED and resistor are limiting. We can look at that quick. So you can see we got about 7.6 there. 510 ohm resistor, it's a 10 volt power supply. The LED drops about 3 volts because it's a blue LED. That gives us about 7 volts left across the resistor. And so we expect about in the range of 14 milliamps of current through the resistor and LED. And there you can see we have pretty much that spot on. So that's what the resistor and the LED want to let through, but the transistor is limiting the current to 7.6. So about 75 or so times as much current. So that is the gain under this circumstance right there. Unfortunately, that is not very reliable. So we have that current going through there, but now I'm going to take that load away, and we are just going to put a jumper directly to the collector right there, and put it in that spot. Now we will measure the current going through here, and you can see it is close. It went up a bit though right there, and I think as the transistor warms up you can see the current's rapidly rising. So there's factors that throw it off, but originally before it heated up it was providing about the same amount of current with no load at all, just a short circuit, as it was with a fairly high load of a 500 ohm resistor, 510 actually, and an LED in series with the collector 2 emitter. So now, after that scene, I turned off the multimeter. You should always turn it off, especially if you're going to measure current. Now, or if you were measuring current, but you should turn it off anyways, as soon as you're done using it, but especially with current. So we are in the microamp range now, because we're going to make a quick change right now. So I'll see how well I can hold this with one hand. And I did have it for a little bit there. Let's try pushing that on the board a little bit more. There we go. So we have about 103 microamp from base to emitter, and so I just have the multimeter probes there. I think you can see them. There we go. So I'm going to just turn this down until that's 100 microamp, till it's 10 microamp. So we'll get 1/10 of the base current, and so just a little tap here now changes the current by quite a bit, because this is pretty low. And there you can see we jumped up. But in any case, I'm going to stick at this till we have 10 microamps. Alright, so I finally got current to about what I want, and it's really hard to get an exact amount of current, and I had to reshoot this scene a few times, so you'll see components in different spots. But there you can see the base to emitter current right here is almost 10 microamps. So I'm just going to say 10 microamps to make everything easier. And now we will grab the LED and put the short lead, the cathode, to the collector there. Long lead, the anode. We're going to connect a 510 ohm resistor again. And just to be safe, we will measure milliamps of current first, even though we know that we can expect only maybe about 75 times as much current. And oh, I put the resistor to the negative rail by accident. There we go, positive rail. Now we should get the current. And there you can see 0.17 milliamps. So that's less than 1. We can definitely put the meter to the microamp range. And there you can see a more accurate reading. We have about 110 microamps, just to make the math easy. So that's the current going through the resistor, LED, the collector to emitter, and ground, plus the current going from base to emitter, which we measured directly was about 10 microamps. So 11 microamps is 100 microamps plus 10 to make the math easy. So we're getting a gain of about 10 right now, but this is really low current. So when you get the gain of a transistor, if you read what the gain is or something, they usually give it to you in a higher current. And so different conditions. In fact, we can see what the current would be without a load. And so the test conditions make a difference, but they'll give you a range of current, and you got to look at the test conditions to really know what all that means. So let's go with milliamps again, just to be safe before we take a measurement. And there you can see 0.17, so we are still safe. Coming down. And there, that one is actually closer to exactly the same than it was at higher current right there. So, in any case, because the transistor is not heating up, so it's probably going to hold better. Alright, so now that's really about it for our demonstration of gain we're going to talk about the setup that I have here a little bit more. So I'm just going to put the emitter directly to ground. We're done measuring current right there, and I'm going to take the LED up there, 510 ohm resistor. So we have a trim pot here. It's a voltage divider right now. We could pop this out and make it a variable resistor. Let's look at going all the way down though. You can see if we go all the way down, we basically have a direct connection from the negative rail and then base there, emitter to negative rail. There's basically a direct connection. There is a diode drop though from base to emitter. Now if I pop the jumper out without short-circuiting anything, there you can see, as a variable resistor, we are no longer to the negative rail. We have 1 kilo ohm. This is a 10 kilo ohm, by the way, 10,000 ohm trim pot. So we're going through the resistive element there, and then to the jumper. And so it is not limiting current, really, at all. It looks like we have enough base current to. We are not saturated. We can tell because of the current there. Well, yeah, we go down and we come up, and you can see current holds pretty steady. So we probably are saturated. And then when we get about here, you see current rapidly rise a bit right at the end there. That's because it's 10,000 ohms of resistance across this element, so 10,000 there, and it lowers. But we also have this 1 kilo ohm resistor in series, and that's why I put that there. Because when I have the trim pot here, without the resistor, if there was a jumper directly to there, we would have a direct connection from the positive rail to that jumper, because that jumper connects to the wiper, to the base, and then the emitter goes directly to ground, and we would probably burn out the transistor. Luckily we have current limited to 30 milliamps, so hopefully we won't, but hopefully we'll see a short circuit and turn off. But in any case, we could. So that's why I have this resistor there, to make sure I never get to the positive rail. But in any case, you can see that this demonstration would not have worked with the trim pot as a variable resistor. This particular one, I'd have to have a much higher value resistor. Whereas if I wire it, I'll try not to block your view, but if I wire it as a voltage divider, then we can get down to 0 volts. And when we do so, there'll be no power. Hopefully that's in the right spot. There'll be no power going through base to emitter, no current going through there. And so we can turn it off completely. So that's another reason why you often see voltage dividers all over the place instead of variable resistors.